Last time we talked about forbidden topological minors. So that was a way for one graph to hide inside another graph, and it was all defined first in terms of subdividing graphs, which is a purely graph theoretic operation, right? You can take an edge in a graph and you produce a new graph that has all the same vertices and edges except that one edge has been removed and replaced with a path of length 2. Purely a combinatorial operation, but we saw that it had topological implications because when you subdivide an edge, you end up with a graph whose geometric realization is homeomorphic to the one you started with. And remember that sometimes for short, we'll just call those two graphs homeomorphic. And so that was an operation on graphs that results in no change in the topology. Now, all of this is leading us towards thinking more about graphs in terms of how we can embed them and draw them in lower dimensional spaces. Now, remember, an embedding is an injective drawing, and a drawing is just a continuous map from the geometric realization into usually the plane, but we can use the same term for embeddings or drawings into, say, three-dimensional space. There's a special case of an embedding or a drawing that we've seen a lot of, and now in this lecture I'm going to make it formal and study it more explicitly, and that's the case of linear embeddings, or really I should say linear drawings. Most of what we'll talk about today are embeddings, but the definition applies to drawings. Now, a drawing was going to just be a continuous map from the geometric realization down into RD, where D, let's just say it's the plane, so R2. In this case, this object that we end up with, this geometric realization of G, it's a subset of that space. So it lives here in RD. And actually, no, it lives up in Rn, where n is the number of vertices, right? So we're mapping it from Rn, usually down into Rd. D could be bigger than n, but in this case, if D is 2, usually that means we have more than 2 vertices and probably n is bigger than 2. So it's a mapping from a high dimensional space to a low dimensional space, and you don't expect such a mapping on the whole space to be injective. But if you just restrict it to this graph, this geometric realization of the graph, it can in fact be injective. Now, the way you would represent a linear mapping, so in this case, F was, we just required it to be continuous in order to be a drawing, but if it's actually linear, that's even better, and linear maps can be represented by matrices, right? So there's some matrix M and D by N, and you can think of this as a function from all of Rn down to Rd. And again, this is not injective, but the restriction to just the geometric realization could be. And we saw that, for example, if you took a kind of a random linear mapping down into R3, that any graph comes out to be embedded that way in R3, just by a linear, sort of a random linear map into 3 dimensions. Now, so this restriction of this linear map is really what we're just calling F, is a linear drawing. So whenever I talk about a linear drawing, this is what I mean. It's a drawing where every vertex is placed at a point and every edge is just a straight line segment, right? And that's a property of linear maps, that straight lines get mapped to straight lines. The edges are straight line segments in Rn, so they map to straight line segments down in Rd. And here again, I've said linear drawing, but this is an embedding if it's injective. All right, so here's an important other fact about this. If I was going to define the linear drawing, it suffices for me to give the positions of the vertices. That is, I just have to say which point each vertex is going to land at, and that will tell me everything I need to know about the drawing. And that makes sense, I think, because, well, if you were going to draw it yourself, once you know where the vertices are, you know that to draw the edge, you just draw a straight line segment. But it's true even more than that if you want to specify the linear mapping or the linear drawing as a matrix. So let's say that my vertices are points here, and let's put them in the plane. Okay, so here's points in the plane, and I want vertex I to go to point pi. That's the goal of this mapping. And so the matrix that I'm going to write just looks like this. It has columns for each point. So here's P0 is a column vector. Pn minus 1, again, is a column vector. And so this would be a 2 by n matrix. And in general, if this is not 2, if it's D, then it's D by n matrix. And it has the property that if I were to simply multiply this matrix times a standard basis vector, pi, I would get pi. Okay, because remember, if you just multiply any matrix times a standard basis vector, it picks out that column. Okay, so it does exactly what we want on the vertices, because remember that the standard basis vectors are the images of the vertices in the geometric realization. And now from this also, we know that if x is in this line segment, bi, bj, up in Rn, then mx is going to map to the line segment pi, pj, down in R2. Okay, so again, this is a subset of Rn. This is a subset of R2. Okay, so the line segments get mapped to line segments. It's perhaps the simplest way to describe a drawing. It also is useful for us for algorithmic purposes, because if you want to encode an embedding, perhaps the simplest way to describe it would be to just say where the vertices go. And we'll see some examples of embeddings that we can get this way. All right. So once we have this notion of a linear embedding, we can define two things which look purely geometric, and they really are geometric ideas, but we could think of them now in terms of graphs, and that will be useful to us. So a polygon then is it's the image of a linear embedding of a cycle. Now, a cycle as a cycle graph, so I can think of it like if P is my linear map, it's mapping from some cycles, let's say on n vertices, into the plane. Okay, and I will use the following notation sometimes, is that I might talk about this as the embedding of P to be in the image of P, because technically here the embedding is the mapping, but often we think of the object that we've drawn as a subset of the plane. That is, it's the image of the mapping, like all the things that get hit by the mapping. Now, similarly, a polygonal path is going to be the image of a linear embedding. And I'm careful to use the word embedding here. Sometimes polygons are allowed to cross themselves, in which case the embedding wouldn't be an embedding, but a drawing. But I'm not going to allow that for now. I'm going to want these are also called simple paths or simple polygons that don't cross themselves. And the linear embedding of a path is going to be just a polygonal path. So think of it like the geometric realization of Pm into the plane. All right. This is going to simplify some ideas for us. It's going to allow us to talk about curves and paths in a really discrete way, because rather than having to consider all possible curves like this, we can just think about ones that take straight lines between points. All right. From these kinds of paths that we have, we can talk about 2 points in a space as a topological space being path connected, and really this is polygonal path connected if there exists some polygonal path that starts at one and ends at the other. So if A and B are 2 points in some space, then a polygonal path, it starts at one of the points, say A, and ends at B. And of course, this path then has to be a path in X. So if I look at a subset, say X might be a subset of RD, I'm looking at a path that actually has to map that path graph into X itself. So let me just make sure I write this here into X. And you can check that this property of being path connected, that is, it's a relation between pairs of points. There either exists a path between them or not. And so that's a binary relation. And there's paths of length 0, so points are path connected to themselves. And so this defines an equivalence relation. And the equivalence classes are called path connected components. I didn't make my box big enough to fit this in here. So the path connected components, and this is in analogy with the connected components in a graph. In fact, the path connected components of an embedding of a graph are the same, or at least in bijection with the connected components of the graph. All right, and so if I have an embedding, then if I look at the path connected components of the complement, so this looks a little bit weird. This is set theory here. So G is the embedding of the graph. So it's a set of points in R2. It's where I've drawn the graph. Here I'm subtracting that out. And I like to think of this as taking a pair of scissors and cutting along all the edges. And if I cut along the edges that I've drawn, the result is R2 minus the embedding. And those are called the faces. And this is our first hint that when you have an embedding of a graph, you get some other objects that are beyond just the vertices and the edges. For example, if I have this embedding of a graph, this graph has 4 vertices and 5 edges. And if I were to take a pair of scissors and cut along the edges that I've drawn, I would end up with 3 faces. There'd be 1, 2, and this one that should not be forgotten outside, the so-called outer face, is number 3. And so we're going to talk a little bit more, or actually quite a bit more, about faces in graphs, and embedded graphs, that is. Now, I want to just wrap up this video by pointing out that there's an assumption we're going to make, and we don't have to make it to be strictly correct, but we're going to make it the following assumption, which is that the drawings are all going to be piecewise linear. So we talked about what it meant to be a linear drawing, but to be piecewise, it means that edges, maybe they're not straight lines, but they're at least drawn as polygonal paths. Polygonal paths are also sometimes called polylines. There's an equivalent way of thinking about this, is that if you have the embedding of this graph into, say, RD, that this map should factor through a linear map. Right, so factoring means, right, that there's 2 maps here. I can actually take, instead of going straight here, I could have taken this geometric realization of G, mapped it into the geometric realization, say, of some other graph, let's call it H, and then this map here is linear. And for practical purposes, you can think of H as being a subdivision of G. Right? So if I took the edges of G, I possibly subdivide them. Now the linear map is going to take those subdivided edges and draw them as polygonal paths. And so why do I do this? Well, we're going to use geometry to prove some topological facts. It's much easier to reason about the geometry sometimes. And some of these topological facts are intuitively obvious, but actually would be no fun to prove. The best example is the Jordan curve theorem, which will be the subject of our next video. If I have a curve like this that closes back in on itself, this is an embedding of a circle in the plane. If I drew this piecewise linear as a polygon, then there's an inside and an outside. That's called the Jordan curve theorem. And believe it or not, it's a little bit tricky to prove that there's always an inside and outside of every one of these polygons, or more generally of any simple closed curve. For polygons, it is going to be easier for us to give a proof, and so we're going to stick to polygons, and we'll see this Jordan curve theorem in the next video.